Hey, what's up guys, my name is Eterno, and welcome to the brilliant maths episode of my Flappy Bird series. Today we'll be talking about maths, a lot. Let's start with vectors. A vector is generally an entity that has a direction and a length. However, commonly in graphics programming, a vector is a way to represent a coordinate. Firstly, we'll need to make a new class which will hold this vector entity. I'm going to right click on the Flappy folder and select New Class. Since vectors directly refer to maths, it makes sense to pop the vector class into the math package, so that all of our maths classes have their own folder in the source code. I'm going to call this class vector3f. The 3 means the vector has 3 components, and the f refers to the data type of the components, in this case, floats. Now as you can see, we have a new folder in our project called math, which is going to hold all of our math stuff. Once we have our class, I'm going to go ahead and create 3 fields at the top which represent the components of the vector, x, y, and z. I'll make them public so that we can easily change them whenever we need. Finally, I'll make a constructor that takes in 3 parameters and appropriately sets the fields to the parameters. This will help us quickly create a new vector when we need to. I'll also make one more constructor that takes in no parameters. This will simply set all the components to 0. Honestly, that's all we need for our vector class. We could write numerous and different operations for our vectors, such as the dot and cross product, reflection and normalization calculations, or even just simply addition and subtraction. But the truth is, we really don't need them for this series. In fact, you could get away without creating this class at all, but it will keep you more organized. What we will need though, without a doubt, is a matrix class. Let's create a new class in our math folder called matrix4f. The 4 means the matrix is a 4x4 matrix holding 16 elements in all. The elements are floats, hence the f. Let's click finish. Matrices are much more complicated than vectors, but they're essentially just an array or a bunch of numbers commonly shown in between 2 large square brackets. They have columns and they have rows. We've made a 4x4 matrix, so we have 16 of those numbers, or elements, in our array. I'm not even going to pretend to explain how matrices work in this video, so if you don't know how they work, I recommend you check out any math textbook or video that talks about matrices. How they work in graphics programming is identical to general mathematics, although graphics programming has certain special types of matrices and equations. As I just mentioned, matrices are essentially arrays. Thus, we'll express our matrix in Java using a public array of floats, which has a size of 16. The reason I wrote 4 times 4 instead of 16 is simply so that the code makes more sense, since this is a 4x4 matrix. Note that this is going to be a single-dimensional array. That's because it will be easier to pass into OpenGL, since OpenGL does not want multi-dimensional arrays. The first thing we'll need to create is an identity matrix. An identity matrix is a special type of matrix in which all elements in the main diagonal are equal to 1, and everything else is 0. This matrix is essentially just the number 1, since when we multiply any appropriate matrix by this identity matrix, it's equivalent to multiplying any single number by 1. So this matrix A, multiplied by our identity matrix, will equal A. The first thing I'm going to do is create a for loop which will fill every element in the matrix with 0. Then I'll need to set the main diagonal elements to 1. To do that, I'll access our matrix array and then use a coordinate system to set the appropriate values. Here I'm setting the first element to 1.0f. Let's take a quick look at this coordinate system. The first number refers to the row of our matrix, the second refers to the column of our matrix, and finally we multiply that by the constant width of our matrix, which is 4. Obviously we could have just written 0 for this one, but writing it out this way makes much more sense. Let's continue with setting each of the elements in our main diagonal to 1. Finally, we'll return this matrix and our identity method is complete. Note that I've made this method static because it returns a new matrix, almost like a constructor. There are 3 main operations we need to give our matrix for this game: multiply, translate, and rotate. Multiplying 2 matrices together isn't as straightforward as you might think. Again, I suggest you read a maths book on this matter to understand it more clearly. Simply put, when multiplying 2 4x4 matrices together, A and B, we take each element from A's rows separately, multiplying it with each element from B's column, and then add them all together. We do this for each of A's rows and B's columns. Since we'll be using column major ordering for our matrices, we need to flip this method. A's columns will be multiplied with B's rows. More on column major ordering later. In this multiply method, we're going to be returning a new matrix that is the result of our current matrix multiplied by the matrix that's in the parameter. To express this more concisely in our code, we can use a for loop, particularly 3 nested for loops as shown here. The first 2 loops go through each of the elements in the row and column, while the third is in charge of multiplying the elements together and adding them to the overall sum of the resulting element, as shown in the equation before. Note the difference in array indices. That's because the first matrix takes elements from its column and multiplies them with the elements in the row of the second matrix. Then we'll return the result of our multiplication. If you don't quite understand how this works, try writing the original equation down on paper and then walk through this code step by step. Paper is where it's at. The translate method is used in graphics programming to move an object around 2D or 3D space. One thing I want to mention straight away is that OpenGL typically takes column major ordering for matrices, as I mentioned earlier, which means that the elements are ordered moving down the column, not across rows. Row major matrices can easily be transposed for use in OpenGL, as you'll see later, but we're just going to go ahead and use column major ordering anyway. What that means is that when we look at the following translation matrix that we need to code, these 3 elements actually refer to the 12th, 13th, and 14th indexed in our array, not the 3rd, 7th, and 11th. Translate will take in a vector, and then set the appropriate elements to the values of that vector, as you saw in the diagram. That's all there is to it. The rotation method is a bit more involved. Firstly, we'll need a bunch of maths operations, so let's scroll up to the top and import Java's math class as static, so that we don't have to type in math dot every time we need something static from the math class. One thing I want to mention is that we really only need z-axis rotation, since this is a 2D game. Because of that, we can use this matrix. But be warned, this matrix only supports rotation along the z-axis. Firstly, Java's math class takes in angles as radians, whereas we as humans would much rather think about degrees. Let's make a variable called r, which converts our angle into radians. We'll need to cast it to a float since Java's 2radians method returns a double. Then we'll simply take the cosine and sine of our fresh radian angle, so that we don't have to keep recalculating it in the future. Now we simply need to set the appropriate elements in the matrix equal to that of the diagram, so let's do the first column first, and then the second column. Now we're ready to return it, and we're done. In case you wanted rotation around all the axes, here's what the implementation of that would look like. The x, y, and z parameters should either be 0 or 1, and they indicate which axes the rotation should occur around. Since we only need z-axis rotation, I'm going to get rid of this method, since we'll never use it in this series. These 2 methods that we just created, translate and rotate, will be used to transform objects in our game, including the map and the bird. Finally, just one more matrix operation remains, the projection matrix. A projection matrix in OpenGL refers to how objects are displayed on the screen. Basically, there are 2 choices, orthographic or perspective. Perspective is similar to orthographic with one main difference. Objects that are further away are rendered smaller, kind of how our eyes see in the real world. Since this is a 2D game, however, we don't need realistic depth, so I'm going to implement the orthographic matrix. Left, right, top, and bottom refer to the clipping margins of our viewport. Basically, they define the margins of the window through which we look into the world. Anything outside these margins is not rendered. Similarly, near and far define the distance at which we render objects. Anything too close or too far, as set by those values, will not be rendered. We'll see this in action soon. Again, we start with the identity matrix, set the appropriate elements as per the diagram, and return the result. And that's all the maths out of the way. LWJGL doesn't take default Java arrays when it sends data to OpenGL. LWJGL wants float buffers instead of float arrays. Also, we're going to need a way to load textures and shaders into the game. Looks like next episode will be all about utility classes. Thanks for watching, and I hope you enjoyed this episode of Let's Make Flappy Bird. As always, a like is greatly appreciated, and I'll see you guys in the next episode. Goodbye.